So this is going to be the chi-square test for homogeneity. This is section 11.2. Test for homogeneity and independence. Most of the time, all the time, you'll be dealing with two-way tables. So one of the first rules of a two-way table is if you see one, please find all of the totals. We call these the marginal totals because they are the totals in the margins. So while you guys are copying this down, I'll be totaling these up for us. So it looks like we have 91 here, 55 here, 192, okay, 113, 109, and 116. And our total should be at 338. So the story behind this is it looks as though they did an experiment where they took moderately depressed people. I think that's what it said. Let me look for it. It was an article in the Journal of American Medical Association. There is reported the results of a study designed to see if the herb St. John's wort is effective in treating moderately severe cases of depression. The study involved these subjects who were being treated for major depression. The subjects were randomly assigned to receive one of three treatments for an 8-week period, and the table at right summarizes the results of the experiment. So I'm not exactly sure what full, partial, and no response. Maybe, they got completely better, they felt really great, or they really didn't feel great at all. So we're going to use this data. And when we begin with our chi-square test, I'm going to start with my HO and my HA. So this is a chi-square test of homogeneity. Homogeneity, prefix meaning the same. So whenever you're doing these chi-square tests for homogeneity, independence, or even goodness of fit, the assumption is always pretty much the name of the test. We assume that all of these samples, these people in the St. John's wort group, the Zoloft group, and the placebo group are all the same, homogeneity. And then the alternative is that they are not the same. So we'll write this out. So HO, there is no difference in the distribution of responses for patients with depression taking St. John's wort, Zoloft, or a placebo. Okay, so the assumption is that they are the same. So there is no difference in the responses for the St. John's wort versus the Zoloft versus the placebo. The alternative is there is a difference. And then we'll just kind of use our dittos. The distribution of responses for patients with depression taking St. John's wort, Zoloft, and placebo. Okay? So our null hypothesis for test for homogeneity, think about what the name of the test is, and that's what your null hypothesis should kind of model. Homogeneity, homo means the same, so there is no difference. Each of the responses for each of these will be the same. Okay, so then we go to our title, and we will write conditions for a chi-square test of homogeneity with, and your degrees of freedom for these two-way table tests, the ones you're going to see for homogeneity and then again for independence, is actually row minus 1 times column minus 1 degrees of freedom. So let me move that over so you guys can see this. So when we look into our rows and columns, so let's go up here. So we have, let's look at our rows. It looks like we have 3 rows and 3 columns. So rows 1, 2, 3, columns 1, 2, 3. So we're going to take 3 minus 1 and 3 minus 1. So it looks like we're looking at 4 degrees of freedom for our conditions. Okay, so you only do it, remember, with a goodness of fit test where you're going to have those, it's categories minus 1, but for these two tests, homogeneity and independence, which look extremely similar, you're going to be doing row minus 1 times column minus 1. So 2 times 2 makes 4. Okay, so now number 1. Hopefully at this point, this isn't the first time it's come into play, but number 1 is you have to check, is it a simple random sample? Well, when you're doing an experiment, you're most likely not going to have a simple random sample. These people are in this experiment because they are depressed. So instead of it being a simple random sample, we just make sure that our people were randomly assigned. So we're going to write treatments I guess in this case, treatments are, the St. John's wort, the Zoloft, and the placebo. Treatments have been randomly assigned. And this would be true for any experiment. You better make sure that you're randomly assigning, people into the treatments or the treatments to the people. So this is the big deal here, is it's not a simple random sample, but we just make sure that this has been a random assignment experiment, completely randomized design, really. And so in this case, I think they stated that. We'll just go with stated in the problem. Maybe you have to assume it. Okay, now number 2 is, normally we have to check, is the population greater than 10 times n? But we only check that if they are sampling without replacement. Well, we're not sampling here. We already have these people, so we don't actually have to write that. What we'll just assume is that, knowing one person's responses should not impact the other patients. So we'll just say, knowing one patient's response should not impact the next patient's. I'll zoom in just a little here so you can see that. Okay, and so for this, therefore, we have independent patients. Okay, now number 3, this is basically the same as the chi-square goodness of fit test, is we need all expected counts to be greater than 5. I guess greater than or equal to at least 5. So for this, now we've got to go back up to our table. And the assumption is that there's no difference between, like what drug you are and what your response is. So we're kind of really looking at, we need these things to be independent. Now, what would happen if we assume there's no difference? These would be very similar. The 113 would be divided equally. And so what I want to show you here is, you don't have to write this down, but just kind of a little review here to help me show you where the expected counts are coming from. So let's say I have just, A and B, and we'll just say male and female. And you don't have to write this down, but here's just a small table. From a long time ago, and I'm hoping, as we start to review, or as you start to review, if independent. So remember when we were proving an independence argument, this is a good review. The probability of A given M would equal the probability of A. Okay, so I'm actually focused on this guy right here. Okay, so what I'm looking at is if these two things, being A and male, are independent, I want to know, what would that number be in there? And so this is kind of the X value that we're looking for. So if independent, okay, so right now it's 2, but let's look for, if they were independent, what it should be. The probability of A given M. So remember, in the given argument, M goes in the denominator. So how many M's do we have? It looks like we have 10. And in the numerator would be A and M, which is right here, and that's actually the X value. Okay, would equal the probability of A, which is 11 out of 31. Okay. So what we're doing here is we're trying to find out what X is. Well, if you were trying to find out what X is, you would take your 10 times 11 divided by 31. Well, if you actually look at what this turns out to be, so now we're looking 31, 10 is the row total times 11 is the column total. And we're going to divide that by 31, which is the total. And I'll write that out so you can see this, total. And that is how you find your expected count. So it's kind of like an independence argument. Is in order to find X, we have this proportion that we can set up, and it's if they're independent, these two things should be true. So up here at the top, we're going to write expected counts. We're going to write this formula equals, we're going to do row total times column total divided by total. So you may want to write that out in your notes just so you know what we're talking about when you go back and look at them. So let me just show you, let me show you a couple expected counts. So let's find the expected count for 27. I'm going to use my red for this guy right here. So what I would do is I would take 91 times, so that's the row total times the column total, 113 divided by 338. Okay, so this is equals, and I'm just going to show you and this is what you should do is, I'm going to have to zoom out. You're going to write expected counts equals, you're going to write the formula, row total times column total over total. And you're not going to show me all of them because that's a little obnoxious, and I'm going to show you an easier way in a moment. But you're going to show me maybe the first and the last. So for the 27, that would be, one second. Oh, I guess just showing me one of them is okay, as long as I see one substitution. But let me show you another one. So for 27, you guys see row total times column total over total. And if I go just to do that in my calculator, 91 times 113 divided by 338 will give me 30.42. Okay, let's do the 66 one, so like right here. So I'm going to take the row total, which is 192, times the column total, which is 116, divide that by the total, which is 338. So 192 times 116 divided by 338 will put me at 65.89. Okay. Now, for the time being, okay, because we get to that third condition, we need all our expected counts to be greater than or equal to 5. So trust me for right now, and we usually, if I was there, I would just have everyone do like, okay, calculate this one, 55 times 109 divided by 338, you know, so trust me right now, I'm going to show you where they're going to get calculated in your calculator, and it'll be really nice, you don't have to worry about it. So trust me for number 3 that we're good, all expected counts will be greater than or equal to 5, and I'll show you where to make sure for that on the calculator. So just like the test for homogeneity, so I'm okay, actually, let's go down here. So therefore, chi-square distribution, distribution is okay to proceed with. Okay, so you're going to draw your normal curve, and we have to put our chi-square value on there. And the chi-square value at the very bottom of page 5, you will, on your grape sheet, you'll find the formula that says chi-square is equal to the summation of observed minus expected squared divided by expected. Okay, so I'm going to show you 2 calculations of this. From the top table, the observed St. John's wort with full response was 27, minus the expected, which was 30.42. Square that divided by your expected, which is 30.42, plus dot, dot, dot. We'll do the last one, so placebo with no response. Observed was 66 minus 65.89 squared divided by the expected, which is 65.99. And here is how you're going to use your calculator. So we're going to need this on the screen and your calculator on the screen. So stat test, and there is your chi-square test. And when you hit your chi-square test, all of you should have this, you're going to see observed and expected, and those are actually matrices. So we have to go into our matrices. And so let me show you how we're going to enter that, or hopefully that doesn't delete, we'll need that. Okay, so second matrix, so second, and then it's right under the math button is the matrix. We're going to edit it, edit. So arrow yourself over to edit, press enter. We have a 3 by 3, don't include the totals. I'm going to enter the matrix, the original matrix, 27, enter 27, 37, 16, 26, 13, 70, 56, and 66 in my calculator, okay? Make sure you're, so second matrix, arrow yourself over to edit, 3 by, press enter, 3 by 3, and just enter your original matrix. Now what's really nice is, so you're going to go into, so right away you're going to enter this in the matrix when you first do the problem. So you're going to go over to stat test, chi-square test, right there. Matrix A has your information in it. What's really nice is when you hit calculate, it's going to do the expected values for you. And and then we have to write them in the tables. So hit calculate. Let's copy down this information that we need. So our chi-square value is 8.72. So I'm going to write that down here. 8.72. We need our p-value equals 0.069. And so let's go up here because this is important. You have to make sure that you do this. once you do the chi-square test, which, you know, you probably just do this right away and then go do your conditions. But so let's go into second matrix again and go into matrix B and edit it. And what's really nice in matrix B is this actually gives you the expected counts that you need. So I'm going to copy these down into my table. So 29.346, 31.23, 18.38, 17.7, 18.87, 64.19, 61.91, and 65 points. So you guys can see that. You have to copy this down. So it's nice because you don't have to do like by hand, row total times column total over total total. Just have to show a couple. And then once you do the chi-square test, you go into your matrix B and it will have the expected counts. You need to write these down so that the third condition has been verified. Notice all of the expected counts are greater than or equal to 5. So we're good to go. Okay, so last part, we got our p-value, got our chi-square value, 8.72, and let's make a conclusion. And I'm running out of room on my paper. So since the p-value is greater than alpha equals 0.05, what am I writing? We fail to reject HO. And we did not gather enough evidence. There is not sufficient evidence to conclude the distribution of responses is not, or I should say, there is not sufficient evidence to conclude, and let me go back to what we wrote. There is a difference in the responses for the three treatments. Sorry, getting sloppy. Hopefully at this point you guys are good at doing this, so shouldn't be too worried. So since the p-value is greater than alpha equals 0.05, we fail to reject HO. There's not sufficient evidence to conclude, basically the alternative, that there is a difference in the responses for the three treatments. So it doesn't look like St. John's wort versus placebo versus Zoloft is doing much. So, okay, and that is a chi-square test for homogeneity. Now, tomorrow you guys will be seeing a chi-square test for independence. It's going to look almost identical. What you guys have to remember, though, is when you're doing a chi-square test for homogeneity, it's all about having different samples. So we have one sample we're comparing to another sample, which we're comparing to another sample. So when I go to, let me write this down, I'll do this up here. So the question always is, which test am I doing? Well, let me get it here. Okay, if you have one sample and one variable, okay, so one sample, one variable, this is a goodness of fit test, GOF. Okay, so one sample, yesterday we did the example with M&M colors. One sample was taken, the colors was the variable, we were doing a goodness of fit. Now, if you see, and this is important, 2 or more samples, with 2 variables, that is a test for homogeneity. Okay. Independence, what you're going to find is it's 1 sample was taken, 2 variables are what you're trying to compare to each other, and that's what's going to make it independence. Okay, that can be a little confusing because homogeneity and independence looks almost identical. It's basically how you take your samples. In this problem, I'm trying to compare St. John's wort to Zoloft to placebo. I'm not comparing responses to the drug. Okay, so it's kind of the way you word the question is the big deal. Okay, so that is it, and we will then do a chi-square test for independence tomorrow. Have a good day, guys.